Somewhere out past the last of the sun's warmth, a spacecraft built in the 1970s is still moving away from us at about 17 kilometers every second. Voyager 1 has been flying for almost 50 years. It crossed the place where the solar wind finally stops and the wind between the stars begins, and most headlines that week said it had left the solar system. It had not left the solar system. The sun's gravity still holds it, and will keep holding it for roughly 30,000 more years, which is simply how long Voyager 1 needs to pass through the vast shell of frozen comets that marks the sun's true border. That is the honest shape of leaving, and it is what these 2 hours are about. The arithmetic of rockets, the stubbornness of light, and a universe that is quietly drifting out of reach while we decide. If the quiet parts of space are the parts you like best, subscribe, and there will always be another long night like this one waiting for you. Voyager 1 is currently about 170 times farther from the Sun than the Earth is. That number is easy to say and hard to hold. If you shrank the distance between the Earth and the Sun down to the length of a single footstep, Voyager 1 would be standing about 170 footsteps away, which is most of a city block, while everything you have ever touched sits within that first step. Radio waves travel at the speed of light, and they still need close to a full day to cross the gap. When engineers on Earth send a command, they wait almost 47 hours for the answer to arrive. Nobody is having a conversation with Voyager 1. They are exchanging letters across a widening ocean. It is moving away at about 17 kilometers every second. That works out to roughly 61,000 kilometers an hour, which means that in the time it takes to read this sentence, the spacecraft has travelled the distance from London to Paris. It has been doing that without pause since 1977. Nothing pushes it. Its thrusters fire only in short puffs to keep the antenna pointed at Earth. The rest is momentum, borrowed once and never given back. The spacecraft itself is smaller than most people imagine. It weighed about 825 kilograms at launch, close to the weight of a small car, and most of that mass is addition tenor 3.5 meters wide. A boom carrying instruments, and a cluster of tanks and boxes wrapped in gold-coloured thermal blanket. Bolted to the side is a gold-plated copper phonograph record with greetings in 55 languages and the sound of a human heartbeat pressed into its grooves. It has no camera pointed forward. It has no destination. Its electricity comes from heat. 3 generators hold pellets of plutonium-238, which is warm because it is decaying, and thermocouples turn a little of that warmth into current. At launch, the generators produced about 470 watts, less than a hairdryer. The plutonium loses half its atoms every 87.7 years, so the supply falls by about 4 watts annually, and the loss is relentless. Engineers have been switching off instruments and heaters one at a time for decades, a slow triage carried out by people, many now retired, who first learned this machine when it was new. Within a few years, the power will fall below what any instrument needs, and the transmitter will go quiet, and Voyager 1 will keep going exactly as it was going before. Here is the part that matters for everything ahead. In August of 2012, Voyager 1 passed out of the bubble of particles blown outward by the Sun, and nearly every headline that followed announced that a human machine had left the solar system for the first time. Voyager 1 did not leave the solar system. It is still falling around the Sun. The Sun's gravity has a grip on it, and will keep that grip, and by the best current estimate, Voyager 1 needs something like 30,000 more years to travel beyond the outermost objects the Sun still holds. That gap between what we said and what is true is not a mistake in the reporting. It is the honest shape of the problem. Leaving is not a line you cross. It is an amount of speed you either have or do not have, measured against a well so deep and so wide that the fastest thing we ever launched is still, after half a century, climbing the near side of it. The Sun does not simply shine, it leaks. A steady stream of charged particles, mostly protons and electrons stripped apart by the heat of the corona, escapes the Sun's gravity and flows outward in every direction at something like 1.5 million kilometers an hour. This is the solar wind, and it never stops. It inflates a bubble around the Sun in the same way a slow leak inflates a balloon, and the wall of that balloon is where the outward push of the wind finally balances against the thin gas drifting between the stars. That balance is not gentle. Somewhere around the orbit of Neptune and well beyond it, the wind slams into the resistance ahead and slows abruptly from supersonic to subsonic, heating and compressing as it does. The boundary where that happens is called the termination shock. Voyager 1 crossed it in December of 2004, 94 times the Earth's distance from the Sun. Voyager 2 crossed it in August of 2007 at 84, and the difference between those two numbers is itself a piece of science, because it means the bubble is not a sphere. It is pushed in on one side like a windsock in a breeze. Past the shock, the wind slows and turns and piled up in a turbulent region, and then it stops entirely. That outer wall is the heliopause. Voyager 1 reached it on the 25th of August 2012, and the strange thing is that nobody knew for over a year. The instrument that should have measured the crossing directly, the one that samples the plasma streaming past, had failed on Voyager 1 back in 1980. So the team led by Don Gurnett at the University of Iowa had to listen instead. Their plasma wave instrument could not measure the surrounding gas at rest, but if the gas were rung like a bell, it would vibrate at a frequency set by how densely its electrons are packed. In March of 2013, a wave from a solar eruption that had left the Sun a year earlier finally washed over the spacecraft, and the gas around it rang. Gurnett's team read the pitch. The electrons were about 40 times more crowded than anything inside the bubble, roughly 0.08 of a particle per cubic centimetre, which is still an emptiness beyond any vacuum made on Earth, and yet unmistakably not the Sun's wind. Working backward through the radiation data, they found the moment. On that August day, the count of solar particles had dropped almost to nothing over a matter of days, and the count of cosmic rays arriving from the wider galaxy had jumped by a few percent and stayed high. Voyager 1 was outside. Voyager 2 confirmed the whole picture on the 5th of November, 2018, at 119 times the Earth-Sun distance, and because its plasma instrument still worked, it measured the crossing as it happened. One expectation failed. The magnetic field beyond the heliopause was supposed to swing to a new direction, the direction of the galaxy's field rather than the Sun's. It barely turned at all. The two fields appear to be draped and connected in ways nobody predicted, and that puzzle remains open today. So a real border was crossed, and it was a border of particles and magnetism, the edge of the Sun's breath. It was never the edge of the Sun's reach. Gravity does not care where the wind stops. Gravity extends without limit, weakening but never vanishing. So the Sun's true territory has to be defined by something other than a fence. It is defined by what still belongs to it, and what still belongs to the Sun is a shell of frozen bodies so enormous and so faint that no telescope has ever directly seen a single one of them in place. The reasoning began with comets. Long-period comets arrive on enormous stretched orbits, blaze around the Sun once, and vanish back into the dark for thousands or millions of years. In 1932, the Estonian astronomer Ernst Öpik argued that such comets must come from a distant reservoir of debris still gravitationally bound to the Sun. In 1950, the Dutch astronomer Jan Oort took the orbits of the comets then known and did something quietly decisive. He calculated how far out each one had been before it fell inward, and he found that their farthest points clustered, again and again, somewhere around 20,000 times the Earth's distance from the Sun and beyond. He also noticed that they came from every direction equally, not from the flat plane the planets share. That is the signature of a shell rather than a disk. The Oort Cloud, as it came to be called, is now understood to begin a few thousand times the Earth's distance from the Sun, and to extend outward perhaps 100,000 times that distance, and by some estimates farther. A light year is a little over 63,000 times the Earth-Sun distance, which means the outer Oort Cloud reaches something like 1.5 light years from the Sun. Alpha Centauri, the nearest star system, lies 4.2 light years away. The Sun's cloud and the cloud around its neighbours may nearly touch. Inside it are comets, and the estimates run to trillions of them. Dark bodies of water ice and frozen carbon monoxide and methane and dust, most only a few kilometres across, orbiting so slowly that a single lap can take millions of years. Their combined mass is probably no more than a few times the Earth's. They are spread so thinly that a comet's nearest neighbour is typically tens of millions of kilometres away. If you stood on one, you would see no others. You would see the Sun as a very bright star, bright enough to cast a faint shadow, and nothing else. Nobody has photographed the cloud. The evidence is entirely in the arrivals. Comet Hale-Bopp, brilliant in the skies of 1997, came from a few hundred times the Earth-Sun distance out. Comet Bernardinelli-Bernstein, discovered in 2021 and larger than any comet previously measured, swings out to roughly 40,000. And in 2003, astronomers found Sedna, a reddish world about 1,000 kilometres wide, which never comes closer than 76 times the Earth's distance and travels out past 900, an object apparently pried loose from the inner part of the cloud that Jack Hills proposed in 1981. These bodies are gravitationally bound to the Sun. They orbit it. They return. By every definition astronomers actually use, they are part of the solar system. Which means that when Voyager 1 crossed the heliopause at 121 times the Earth's distance from the Sun, it had covered roughly 1 part in 1,000 of the distance to the far edge of the Sun's family. The wind stops early. The gravity keeps going. Put a number on how much farther Voyager 1 has to travel, and the scale of the problem stops being poetic and becomes arithmetic. NASA's own estimate is straightforward. At its current speed, Voyager 1 will take about 300 years just to reach the inner boundary of the Oort Cloud. Passing all the way through it will take somewhere near 30,000 years. 300 years ago, Isaac Newton had been dead for less than a decade. 30,000 years ago, people were painting horses and lions on the walls of Chauvet Cave in southern France, and there were still Neanderthals somewhere in Europe. The whole of recorded history from the first cuneiform tablets to this moment fits inside that span roughly 5 times over. For that entire stretch, Voyager 1 will remain gravitationally bound to the Sun. Not in orbit exactly, because it is moving fast enough that it will never come back, but bound in the sense that the Sun is still the dominant body pulling on it, still the thing it is receding from rather than a thing it has escaped. Astronomers have a name for the region where one body's gravity beats out the pull of everything else, and it is called the Hill Sphere, after the American astronomer George William Hill. Around the Sun, the balance is struck against the combined gravity of the Milky Way, all those hundreds of billions of stars, and the point where the two are equal lies somewhere between 1 and 2 light years out. That is the Sun's actual sphere of influence. It is roughly the size of the Oort Cloud, which is not a coincidence, because the cloud is simply the material the Sun managed to keep. Voyager 1 is currently about 1/400th of a light year from home. There is something clarifying in that fraction. The spacecraft is often described as the most distant human object, which is true, and as an interstellar probe, which is also true in the narrow sense that it is now flying through interstellar gas rather than solar wind. But if you stepped far enough back to see the Sun's whole domain at once, the way you can see a raindrop hole, Voyager 1 would not be visible near the edge. It would be a speck buried near the very centre, having barely begun. The word we use for what happens at the end of those 30,000 years is escape. It has a precise meaning. An object escapes when its speed exceeds the escape velocity at its distance, which is the speed at which kinetic energy exactly balances the depth of the gravitational well. Voyager 1 has that speed. It cleared that threshold decades ago. At Jupiter and Saturn, it is going to escape. So the difficulty is not whether we can throw something out of the Sun's grasp. We have done it 5 times. The difficulty is how slowly the throw travels, and how long the escape takes, and what that means for a species with a lifespan of decades and a civilization that has been writing things down for about 5,000 years. Escape, it turns out, is cheap. Escape at any speed worth having is not. Everything that follows in this script grows out of that single distinction. and the first place to see it clearly is in the small fleet of objects that have already made it out the door. 5 spacecraft are leaving. That is the entire list, and it will remain the entire list for a long time, because nothing currently built or funded will join it. Pioneer 10 launched on the 2nd of March 1972 and became the first machine to cross the asteroid belt and the first to fly past Jupiter. Its swing around that planet in December of 1973 left it moving fast enough to leave the Sun behind, and it is now travelling at about 12 kilometers per second relative to the Sun. Its last faint signal reached Earth on the 23rd of January 2003 from about 80 times the Earth's distance. The spacecraft carries a gold anodized aluminum plaque designed by Carl Sagan and Frank Drake and drawn by Linda Salzman Sagan, showing a man and a woman and a map of our position among 14 pulsars. Pioneer 11 followed on the 6th of April, 1973, used Jupiter to fling itself across the solar system to Saturn, and became the first spacecraft to see that planet up close. It carries the same plaque. Its transmitter was last heard in November of 1995. It is moving at roughly 11.5 kilometers per second, headed in the general direction of the constellation Aquila. Then the Voyagers, launched 16 days apart in 1977, with Voyager 2 going first on the 20th of August, and Voyager 1 following on the 5th of September and overtaking it in space. Voyager 1 is the fastest thing we have ever sent away from the Sun, at about 17 kilometers per second. Voyager 2, which took the longer road past Uranus and Neptune, is doing about 15.5. Both are still transmitting. The 5th is New Horizons, launched on the 19th of January 2006, on an Atlas V with a third stage bolted on, and it left Earth faster than any spacecraft before or since, at roughly 16 kilometers per second. It reached the Moon's distance in 9 hours. It flew past Pluto in July of 2015 and past a small contact binary body named Arakoth on New Year's Day 2019. It is still working, still returning data on the dust and the ultraviolet glow out where it flies, and it is currently past 60 times the Earth's distance from the Sun. Notice what has happened to its speed. New Horizons left Earth faster than Voyager 1 and is now the slowest of the two, moving at about 13 kilometers per second. It has spent 20 years climbing out of the Sun's gravity well, converting speed into distance, the way a ball thrown upwards slows as it rises. Voyager 1 is faster now because of what happened at Jupiter and Saturn, not because of what happened at the launch pad. Every one of these 5 spacecraft, without exception, owes its escape not to its rocket but to a planet. None of them is aimed at a star. They were aimed at Jupiter, at Saturn, at Pluto, and the direction they left in was whatever direction the geometry handed them. They will drift for tens of thousands of years, cold, silent, essentially indestructible in a place with nothing to erode them, carrying pictures and recordings that will almost certainly never be found. And to understand how even that modest speed was achieved, you have to understand a trick that seems, at first hearing, like it should not work at all. In 1961, a graduate student named Michael Minovich was spending his summer at the Jet Propulsion Laboratory in Pasadena, with access to an IBM 790, then one of the fastest computers on Earth. He was working on the three-body problem, the ancient headache of calculating how 3 masses move under mutual gravity, and he began asking what happened to a spacecraft's speed when it passed close to a planet. The intuition most people have is that nothing should happen. The planet pulls the spacecraft in, which speeds it up, and then the spacecraft climbs away again, which slows it down by exactly the same amount. Energy in, energy out. Relative to the planet, that is precisely correct. A spacecraft approaching Jupiter at 10 kilometers per second leaves Jupiter at 10 kilometers per second. It has only changed direction. But the planet is not standing still. Jupiter is moving around the Sun at about 13 kilometers per second, and what matters for escaping the Sun is the spacecraft's speed relative to the Sun. If you arrange the flyby so that the spacecraft leaves in the same direction Jupiter is travelling, then in the Sun's frame you add most of that 13 to your own speed. The spacecraft has stolen a little of Jupiter's orbital motion. It really is theft, and it obeys conservation of momentum exactly. Jupiter slowed down. Voyager 1 took energy from it, and Jupiter paid, and because Jupiter is 318 times the mass of Earth, the payment was a slowing so small that it could not be measured with any instrument that will ever exist. Something like a fraction of an atom's width per year of orbital drift. Minovich worked the numbers and found that a spacecraft could be routed from planet to planet, gathering speed at each, with almost no fuel. He was largely disbelieved at first. In 1965, another young researcher at JPL, Gary Flandreau, was studying the outer planets and noticed that Jupiter, Saturn, Uranus, and Neptune would fall into a rough line in the late 1970s. A single spacecraft could hop along all four, and the flight to Neptune, a journey of 30 years by direct route, could be done in 12. The first real use came in 1974, when Mariner 10 swung past Venus to reach Mercury, a trip that was flatly impossible with the fuel it carried. Then the pioneers used Jupiter. Then Voyager 1 arrived at Jupiter in March of 1979, moving at about 10 kilometers per second and departed at about 16. Then took another push from Saturn in November of 1980, and came away on the trajectory it is still following. The important thing to hold on to is where the speed came from. It came from a planet's orbital motion around the Sun, which was itself set 4.5 billion years ago when the solar system formed. Every kilometre per second Voyager carries is an inheritance. The rocket that launched it contributed almost nothing to its final velocity. That is a wonderful trick and a hard ceiling. There are only so many planets. They're only moving so fast, and they only line up when they line up. The alignment that made the Voyagers possible was not a convenience. It was a lottery ticket, and it had a date on it. The 4 giant planets take different amounts of time to circle the Sun. Jupiter needs just under 12 years, Saturn about 29.5, Uranus about 84, and Neptune about 165. For a single spacecraft to visit all 4 in one continuous chain of gravity assists. They must be strung out along an arc in the right order, so that each planet is waiting in the right place when the spacecraft arrives, having been thrown there by the previous one. Work out how often that arrangement recurs, and the answer comes to roughly 176 years. The last time the outer planets stood in that order before the Voyagers, Thomas Jefferson was in the White House. Napoleon was consolidating power in France, and the planet Neptune had not been discovered and would not be for another 4 decades. Nobody could have used the alignment. Nobody knew it was there. The time before that, Isaac Newton was a young man, and the laws that described the alignment had not yet been written down. Gary Flandreau found the next one in 1965, and it fell in the late 1970s, which meant that humanity's ability to build interplanetary spacecraft and the sky's willingness to permit a grand tour overlapped by a margin of about 15 years. We had learned to launch things into space in 1957. We would have missed the window by a single lifetime. NASA nearly missed it anyway. The original Grand Tour proposal was expensive, and it was cancelled in 1972 in favour of a cheaper program to send 2 spacecraft to Jupiter and Saturn only. The engineers built them for more than that anyway, quietly over-designing the electronics and the radiation shielding, and when Voyager 1's Saturn encounter succeeded, Voyager 2 was released to continue. It reached Uranus in January of 1986, and Neptune in August of 1989. It remains the only spacecraft ever to have visited either world, and given how planning cycles run, it will probably hold that distinction for decades more. There is a temptation to read that story as luck, and the luck is real. But the deeper lesson is about dependence. The fastest departures we have ever managed required the outer planets to be arranged in a particular way. Our best trajectory out of the solar system was not designed. It was found lying on the ground, and we picked it up. The next comparable alignment arrives in the middle of the 22nd century. A spacecraft launched then, using the same trick with better engineering, might leave at 20 or 25 kilometers per second instead of 17. It would still need something like 20,000 years to reach the distance of the nearest star. doubling Voyager's speed does not open the door to the galaxy. It shortens an impossible journey into a slightly less impossible one. Everything in that arithmetic points back to one question, which is why the rocket itself contributes so little. A Titan IIIe stood 38 meters tall and burned for minutes. Voyager weighed less than a small car. Almost the entire mass on that launch pad existed to lift the rest of the mass on that launch pad, and the payload that finally left was a rounding error. That is not a failure of engineering. It is a consequence of a single equation, written down more than a century ago by a deaf schoolteacher in a provincial Russian town, and no amount of cleverness has ever loosened it. Konstantin Tsiolkovsky was born in 1857 in the Ryazan region of Russia, lost most of his hearing to scarlet fever as a boy, was largely self-taught in libraries, and spent his working life teaching mathematics in the town of Kaluga. He built a wind tunnel in his apartment. He wrote science fiction. In 1897 he derived, and in 1903 published, the equation that governs every rocket that has ever flown or ever will. The idea underneath it is simple enough to state without any mathematics. A rocket has nothing to push against. There is no air behind it and no ground beneath it. The only way it can change its speed is to throw part of itself backward, hard, and ride the recoil. Every kilogram of exhaust flung out the nozzle buys a small increment of speed for everything that remains. The trouble is what everything that remains includes. It includes the fuel you have not burned yet. To go faster, you carry more fuel, but the extra fuel is itself mass that has to be accelerated by the fuel beneath it, which means you need still more fuel to accelerate that, and the pile grows on itself. Tsiolkovsky's equation captures this exactly. The speed you can gain equals the speed of your exhaust, multiplied by the natural logarithm of the ratio between your starting mass and your final mass. The logarithm is the whole story. It is a function that grows very slowly, which means its inverse grows very fast. If you want a final speed equal to your exhaust speed, you need a mass ratio of about 2.7. If you want twice your exhaust speed, the ratio jumps to about 7.4. 3 times, and you need about 20. 10 times your exhaust speed, and the ratio is more than 22,000 to 1. Sit with that last figure. To reach 10 times your exhaust velocity, 99.995% of everything on the launch pad has to be propellant, and the payload has to fit in what is left. There is no engineering refinement that touches this. It is not about materials or nozzles or combustion efficiency. It is a statement about momentum, and it would hold on any planet in any universe with the same conservation laws. Everything about rocketry that seems strange makes sense in this light. Staging exists because carrying an empty tank costs you speed, so you throw the tank away the moment it is dry. The Saturn V weighed about 2,970 tons on the pad and delivered around 45 tons to the Moon, which is roughly 1.5%. A modern launch vehicle putting a satellite into low orbit is doing well to deliver 4% of its liftoff mass. The rest is propellant and structure and discarded shells falling into the sea. Tsiolkovsky understood the implication before anyone had launched anything. He wrote about multi-stage rockets, about liquid hydrogen and liquid oxygen as propellants, about space stations and airlocks and growing food in orbit, decades before any of it was possible. He also understood that the equation contains one obvious escape route, and it is not in the mass ratio at all. It is in the exhaust velocity. Make the exhaust faster, and the whole punishing logarithm gets multiplied by a bigger number. Every serious idea for reaching another star is, in the end, an attempt to do exactly that. A chemical rocket engine is a controlled fire in a pipe. 2 substances meet, they react. The reaction releases energy stored in the bonds between atoms, and the hot gas escapes through a nozzle that converts random thermal motion into directed flow. The speed of that flow is set by how much energy each kilogram of exhaust carries and how light the exhaust molecules are. Both of those numbers have ceilings, and the ceilings are set by chemistry itself. The most energetic practical combination we use is liquid hydrogen burned with liquid oxygen, which is what powered the upper stages of the Saturn V and what still powers the space shuttle's descendants. It produces water vapour, a light molecule, at very high temperature. Its exhaust leaves the nozzle at about 4.4 kilometers per second in vacuum. Kerosene and oxygen, the workhorse combination used by the Falcon 9 and the Soyuz, manages about 3.5. Solid boosters, less. Exotic mixtures involving fluorine or beryllium can push toward 5 at the cost of exhaust so toxic and corrosive that nobody flies them. That is essentially the whole range. Chemical bonds hold a certain amount of energy, on the order of a few electron volts per atom, and no rearrangement of the periodic table will get you meaningfully past 5 kilometers per second of exhaust. It is a hard number written into the structure of matter. Now, bring back Tsiolkovsky. To leave the Sun's neighbourhood at a speed that would reach Alpha Centauri in a human lifetime, you want perhaps 10% of light speed, which is 30,000 kilometers per second. Divide that by an exhaust velocity of 4.4, and you need a delta V about 6,800 times your exhaust speed. Raise the number 2.7 to that power, and the mass ratio is not large. It is not astronomically large. It is a number with roughly 3,000 digits in it, which exceeds the number of atoms in the observable universe by a margin so vast that the comparison stops meaning anything. Even a modest goal collapses. Suppose you were content with 1% of light speed, 3,000 kilometers per second, arriving at the nearest star in 420 years. The mass ratio would still be a number with hundreds of digits. Suppose you wanted merely to double Voyager 1's speed by rocket power alone, without a planet's help starting from Earth orbit. That is achievable, barely, with a very large vehicle and a very small payload. This is why the Voyagers went to Jupiter first, and why New Horizons, launched on the most aggressive escape trajectory ever flown, is now the slowest of the 5 departing craft. It is why interplanetary missions are planned around alignments and years of coasting rather than around burning harder. Chemical propulsion took us to the Moon, and it will take us to Mars, because those are places within a few kilometers per second of where we already are. The stars are not a few kilometers per second away, they are tens of thousands. Every proposal that follows in this script accepts that chemistry is finished and looks for exhaust that moves faster. Nuclear fission gives you perhaps 10 times the energy density. Fusion, 1,000 times more. Antimatter, everything the mass has. And light itself, which needs no exhaust at all. But before any of those, there is a subtler question about where you fire the engine you have, because the Sun's own gravity well turns out to contain a loophole. To leave the Earth's surface and never fall back, ignoring the atmosphere, you need to be moving at 11.2 kilometers per second. That is the escape velocity from Earth, and it does not depend on which direction you point, only on speed. Straight up, sideways, at any angle that clears the ground, 11.2 is the price. To escape the Sun from where the Earth orbits, you need 42.1 kilometers per second. Those two numbers side by side explain why the Moon is a weekend and the stars are forever. The Sun's well, at our distance, is nearly 4 times deeper in terms of speed and more than 14 times deeper in terms of energy, because energy scales as the square. But there is a gift built into our situation. The Earth is not sitting still in the Sun's well. It is orbiting at 29.8 kilometers per second, which means anything launched from Earth is already carrying that speed for free. A spacecraft that leaves Earth's gravity entirely and does nothing else finds itself in the Sun's grip, moving at about 30 kilometers per second. To escape the Sun, it needs only the difference, roughly 12.3 kilometers per second more, and it needs it in the right direction, which means launching in the direction of Earth's motion around the Sun and timing the departure to the season. Combine the two requirements properly, and a spacecraft leaving Earth's surface needs about 16.6 kilometers per second to escape the entire solar system, assuming it aims its departure perfectly along Earth's orbital path. New Horizons left at about 16.26, which is why it is on an escape trajectory. It is also why, 20 years later, it has slowed to 13. It cleared the fence with almost nothing to spare and has been paying for the climb ever since. There is a mirror image problem that surprises people. Reaching the Sun is harder than leaving it. To fall into the Sun from Earth's orbit, you would have to cancel that same 29.8 kilometers per second of sideways motion, which is more than twice the speed needed to escape outward. This is why the Parker Solar Probe, which we will come to, needed 7 flybys of Venus over 6 years, simply to shed speed and fall closer, and it is why the geometry of the outer planets mattered so much. Jupiter orbits at 13 kilometers per second, and a well-designed flyby can hand a spacecraft most of twice that in the Sun's frame, depending on approach angle. That single encounter is worth more than any chemical stage humanity has built. Now sit with the shape of the well itself. Escape velocity from the Sun falls off as you move outward. At the Earth's distance, it is 42 kilometers per second. At Jupiter, about 18.5. At Neptune, about 7.5. Out where Voyager 1 is now, at 170 times the Earth's distance, escape velocity has dropped to a little over 3 kilometers per second. Voyager 1 is moving at 17. It is comfortably free, and the surplus it carries is what will eventually take it out of the Oort Cloud. Run that logic in the other direction and something interesting appears. If escape velocity is low far from the Sun and high close to it, and if you must burn fuel somewhere, then the place where a burn buys you the most is not out at the edge where escape seems easy. It is down at the bottom, where the Sun is a furnace and the spacecraft is moving fastest. That inversion has a name, and it belongs to a German school teacher who was rejected by the university he wanted to attend. Hermann Oberth submitted his doctoral thesis on rocketry to the University of Heidelberg in 1922, and it was rejected as too speculative. He published it himself the following year under the title The Rocket into Planetary Space, and a fuller version in 1929. Inside that later book is a passage describing something that reads, "On first encounter, like a violation of energy conservation." The point is this: a rocket's engine delivers a fixed change in speed for a given amount of fuel regardless of how fast the rocket is already going. But the useful thing is not speed, it is energy, because energy is what determines whether you escape and how much surplus you carry away. Energy rises as the square of speed. Adding 1 kilometer per second to a spacecraft already moving at 1 kilometer per second triples its kinetic energy. Adding 1 kilometer per second to a spacecraft moving at 50 barely changes the energy in percentage terms, but the absolute gain is enormous because you are working on the steep part of a curve. So the deeper you are in a gravity well when you fire your engine, the faster you're already moving, and the more energy each kilogram of fuel delivers to the vehicle, rather than being wasted in the exhaust. This is the Oberth effect, and it is why interplanetary probes burn at the closest point of their orbits rather than the farthest. Follow it to its conclusion, and you get a strange, beautiful trajectory. Take a spacecraft, send it out toward Jupiter, let Jupiter's gravity turn it and cancel most of its orbital motion so it falls almost straight back toward the Sun. It dives inward, accelerating, and at its closest approach it is moving at hundreds of kilometers per second. There, skimming the corona, it fires its engine. The Oberth effect multiplies the benefit, and the same fuel that would have brought a modest speed increase out at Earth's orbit instead flings the spacecraft outward at speeds no other maneuver can reach. The concept is called a solar Oberth maneuver, or more evocatively a sun diver. Studies from Johns Hopkins Applied Physics Laboratory, looking at a proposed interstellar precursor mission to reach 1,000 times the Earth's distance from the Sun, found that a sun diver passing within a few solar radii could achieve 20 kilometers per second or better, potentially much better, with a large enough burn. It is, on paper, the single most efficient way to leave the solar system with chemical propulsion. The obstacle is heat. At a few solar radii, the sunlight is thousands of times more intense than at Earth, and the spacecraft must survive it while carrying cryogenic propellant, which wants to boil, and while performing the most precisely timed burn in the mission at the exact moment the shield is under maximum load. The engineering is not obviously impossible. It has simply never been done, and no funded mission plans to do it. What we have done instead is send something into the sun's furnace without a rocket to see what is there. It flies faster than any object humans have ever made, faster by a wide margin than Voyager 1 ever travelled, and it is not going anywhere at all. The Parker Solar Probe launched on the 12th of August 2018 on a Delta IV Heavy with a Star 48 upper stage, one of the most powerful configurations ever assembled, and it needed all of it because it was trying to fall toward the Sun rather than fly away from it. Over the next 6 years, it flew past Venus 7 times, each pass shaving away some of its orbital speed and lowering the closest point of its orbit toward the Sun. On the 24th of December 2024, it passed 6.1 million kilometers above the Sun's visible surface, closer than any object we have built, inside the corona itself. At that moment it was moving at approximately 192 kilometers per second, about 430,000 miles per hour. Light travels 1,560 times faster, which sounds humbling until you realise this thing was covering the distance from New York to Los Angeles in 20 seconds. It is protected by a shield of carbon composite foam, sandwiched between carbon sheets, about 11.5 centimetres thick, coated white on the sunward face. The shield reaches around 1,370 degrees Celsius. Behind it, in the shadow, the instruments sit at roughly room temperature. The whole design is a study in the fact that heat and temperature are different things, because the corona is over 1 million degrees, but so thin that it carries almost no heat into a passing object. Parker has done real science. It flew through structures called switchbacks, sudden reversals in the sun's magnetic field, and traced their origin to the surface. It found the boundary where the sun's magnetic field stops dragging the escaping plasma around with it, the Alphen surface, and it flew above and below that line. It watched the solar wind being born, and here is the point for our purposes. The Parker Solar Probe is the fastest object humanity has ever built, and it is in orbit. Its period is 88 days. It goes around and comes back over and over, and it is as bound to the Sun as the Earth is. Its enormous speed exists only because it is at the bottom of the well, where everything moves fast. Escape velocity right where Parker makes its closest pass is around 270 kilometers per second. Parker, at 192, is well below it. Set the two spacecraft beside each other. Voyager 1 crawls at 17 kilometers per second and is leaving forever. Parker screams past at 192 and will never leave at all. Speed alone tells you nothing. What matters is speed measured against the depth of the well you happen to be standing in, and Voyager, out in the shallows, needed only a little to be free. This is the essential shape of the problem. The sun's well is not a wall you break through. It is a slope that never quite flattens, and a spacecraft that clears it does so with whatever surplus it has left over, which for every machine we have ever launched has been a few kilometers per second. To carry a real surplus tens of thousands of kilometers per second, you cannot climb faster. You have to arrive at the top already, moving at a speed no chemical fire can produce. Which sent a small group of physicists in the late 1950s toward the only energy source then known that was violent enough. They proposed to detonate nuclear bombs behind a spacecraft one after another and ride the shock. The idea belongs first to Stanislaw Ulam, the Polish-American mathematician who had worked on the hydrogen bomb, and who sketched in 1947 the possibility of propelling a vehicle with nuclear explosions. In 1958, at General Atomics in La Jolla, California, a team assembled to take the sketch seriously. Ted Taylor, a bomb designer with an unnerving gift for making fission devices smaller, led it. Freeman Dyson, the British-born physicist, took a year away from Princeton to join him. They called it Project Orion, and the design was as brutal as it was elegant. Behind the ship, a thick steel plate. Behind the plate, a hole through which shaped nuclear charges would be ejected, one every second or so, each detonating a short distance away. the explosion would vaporize a disk of propellant built into the charge, and that plasma would slam into the pusher plate at enormous speed. 2 stages of shock absorbers, the second a set of gas-filled pistons, would smooth the hammer blows into steady acceleration for the crew. It sounds absurd. It works. The exhaust velocity of a nuclear explosion is somewhere between 20 and 100 kilometers per second, depending on the design, 10 to 20 times better than any chemical engine, and unlike almost every other advanced concept, the thrust is colossal. Orion could have lifted thousands of tons from the ground. Dyson liked to point out that it was the only interstellar propulsion scheme buildable with 1950s technology. In November of 1959, they tested the principle at Point Loma with a 1-meter model called Hot Rod, driven by a sequence of conventional explosive charges. It flew about 56 meters straight up and came down on a parachute intact. The pusher plate survived. There is film of it. The team designed a ship and then a larger one, and Dyson eventually published a paper in 1968 called Interstellar Transport, in which he examined what a hydrogen bomb version could do. A vessel massing hundreds of thousands of tons might reach 3 or 4% of light speed. Alpha Centauri in 130 years. Not one human lifetime, but not geological time either. 2 things killed it. The first was fallout. Launching from the ground meant detonating hundreds of small nuclear devices in the atmosphere, and even by the standards of an era that had already conducted hundreds of open-air tests, the estimated casualties from a single launch were not something anyone wanted printed. The second was law. The Partial Test Ban Treaty, signed in 1963 by the United States, the Soviet Union, and the United Kingdom, prohibited nuclear detonations in the atmosphere, underwater, and in outer space. Orion, as conceived, became illegal. Funding ended in 1965. Dyson later wrote that he was relieved, and that he had come to believe the world was better off without a fleet of ships that could carry thousands of tons anywhere in the solar system, and were, in every meaningful sense, also weapons. What remains is a demonstrated principle and a number. Orion is the only interstellar concept that a nation could have built with the industry of 60 years ago. Everything proposed since has been faster, cleaner, and further from anyone's reach. The next serious attempt came from a group of engineers who met on their evenings off in London, and who decided that if fission was too dirty, they would build a starship around fusion instead. Between 1973 and 1978, 13 members of the British Interplanetary Society met in the evenings, unpaid, to design a starship. The engineer Alan Bond led the propulsion work, Anthony Martin edited the results, and they published a full technical study of a vessel they named Daedalus, after the craftsman of Greek myth who built wings and, unlike his son, used them wisely. They gave themselves rules, only physics known to work, no exotic assumptions. The ship must be buildable with technology plausibly available within a few decades. It must reach a nearby star within a working human lifetime and return useful data. What they produced was a 2-stage vehicle, 190 meters tall, weighing 54,000 tons fully fueled. 50,000 of those tons were propellant. The payload was 450 tons of instruments, probes, and a computer intelligent enough to run the mission alone. The engine was inertial confinement fusion. Small pellets of deuterium and helium-3, each weighing a fraction of a gram, would be dropped into a reaction chamber and struck simultaneously by beams of relativistic electrons, compressing and igniting them. The chamber had no walls at the rear. A magnetic field generated by superconducting coils would shape the expanding plasma and direct it backward. 250 detonations every second for years. The choice of helium-3 rather than the easier deuterium-tritium reaction was deliberate. Deuterium and helium-3 fuse into helium-4 and a proton, and both products are charged, which means a magnetic nozzle can grip them. The easier reaction produces neutrons, which are electrically neutral, fly straight through any magnetic field, and cook the ship. The problem is that helium-3 barely exists on Earth. The team proposed mining it from the atmosphere of Jupiter, using aerostat factories held aloft by hot hydrogen balloons, operating for 20 years to gather the required 30,000 tons. That single supporting operation would dwarf anything humanity has attempted in space. The first stage would burn for just over 2 years, then separate. The second would burn for nearly 2 more. At the end, Daedalus would be travelling at about 12% of the speed of light, 36,000 kilometres per second. It would coast for 46 years toward Barnard's star, a red dwarf 5.9 light-years away, chosen because in the 1970s there was tentative evidence of planets there. That evidence turned out to be an artefact of a flexing telescope, though a real planet was finally confirmed around Barnard's star in 2024. The hull would carry a beryllium shield 50 tons thick against the dust it would meet at that speed, and a cloud of particles sprayed ahead of it to break up anything larger. And then, arriving after 50 years, Daedalus would fly straight past. It carried no way to slow down. 18 sub-probes would launch ahead of it, gathering what they could as the system swept by in a matter of hours, radioing everything home across 6 light-years, while the mothership continued into the dark, still moving at 12% of light speed, forever. That was not laziness. Stopping is the part of the problem that makes everything else look easy. Slowing down costs the same as speeding up. That is the first thing to understand, and it is unintuitive because on Earth we stop by pushing against the ground or the air, which is free. In space there is nothing to push against. To shed 36,000 kilometers per second, you must accelerate in the opposite direction by 36,000 kilometers per second, and you must do it with a rocket, and the rocket obeys Tsiolkovsky. The consequence is not that the cost doubles, it is that the mass ratio squares. Suppose a ship needs a mass ratio of 100 to reach its cruising speed. To also stop at the far end, it must carry the fuel for the stopping burn all the way there, which means the acceleration stage has to lift that fuel too. The ship now needs a mass ratio of 100 to arrive, with a fully fueled second ship, which itself has a mass ratio of 100. 10,000 to 1. If it needed 1,000 to 1 for the outbound leg, it now needs 1,000,000. Add the desire to come home again, and the exponent climbs twice more. A round trip with a stop at each end takes the mass ratio to the 4th power. This is why every serious interstellar study since Daedalus has been a flyby, and why the phrase one way appears in them without apology. Project Icarus, a redesign of Daedalus begun in 2009 by an international group of volunteers, made deceleration a requirement from the start, and the ship that came out of it was substantially heavier and slower, roughly 5% of light speed taking a century to reach its target. That is the exchange rate. You buy the ability to stop with time and mass, and you pay dearly. So people look for ways to stop without fuel. Robert Zubrin and Dana Andrews proposed the magnetic sail in 1988, a loop of superconducting wire kilometers across, generating a magnetic bubble that deflects the charged particles of the interstellar medium and drags against them. At relativistic speed, the drag is real, and it needs no propellant. The engineering, which involves maintaining superconductors across decades in deep space and deploying a structure of that size, has never been attempted. There is a more elegant possibility. In 2017, René Heller and Michael Hipke calculated what a light sail could do if it arrived at Alpha Centauri and turned its sail toward the star, letting the starlight push against it. Sunlight decelerates as readily as it accelerates if you approach from the right angle at the right speed. Their answer was that a sail could break into orbit around Alpha Centauri, and then use the light of that star to travel onward to Proxima Centauri and break again. The catch is the speed limit. To be captured rather than blown past, the sail must arrive at no more than about 4.5% of light speed, which stretches the trip to roughly 95 years, and the sail must be almost impossibly light and reflective. Every one of these schemes shares a hope, which is that the ship might get something from its surroundings rather than carrying everything with it. Space looks empty, but it is not perfectly empty, and one physicist looked at the thin hydrogen drifting between the stars and saw a fuel tank 100 light-years wide. Robert Bussard was working on nuclear propulsion at Los Alamos when, in 1960, he published a short paper describing an engine that would never run out of fuel. The reasoning is clean. Interstellar space contains hydrogen, roughly 1 atom per cubic centimetre in the general galactic average. Hydrogen is fusion fuel. A ship moving quickly through that gas sweeps up a great deal of it. So build a scoop, funnel the hydrogen into a reactor, fuse it into helium, and throw the helium out the back. The ship carries no propellant at all. It accelerates for as long as it likes, indefinitely, approaching the speed of light, its crew aging slowly while centuries pass outside. The image was irresistible, and it entered science fiction almost immediately. Paul Anderson built a novel around it. Carl Sagan wrote about it seriously in 1963, calculating that a ramjet could cross the visible universe within a human lifetime as measured aboard. The scoop was always the hardest part. Interstellar hydrogen is mostly neutral, and neutral atoms ignore magnetic fields. Bussard proposed ionizing the gas ahead with lasers, then funneling the resulting protons with a magnetic field. To gather enough at a reasonable speed, the effective scoop must be enormous, thousands of kilometers across at minimum, and by some calculations tens of thousands. Then there is the reaction itself. Stars fuse ordinary hydrogen through the proton-proton chain, and the first step requires 2 protons to collide and, in that instant, for one of them to undergo a weak force conversion into a neutron. The weak force is slow. In the core of the Sun, an individual proton waits on average about 1 billion years for this to happen, and the Sun shines only because it contains an unimaginable number of protons. No engine can wait. Bussard's ramjet needs a reaction rate that the underlying physics does not offer. But the fatal blow came from the scoop. In 1989, Zubrin and Andrews ran the numbers on the drag. Every proton the scoop captures must be accelerated from rest, in the ship's frame, to the ship's own speed before it can be usefully burned. That takes momentum out of the ship. They found that for any plausible scoop design and any plausible fusion efficiency, the drag on the magnetic field exceeded the thrust the reactor could produce. The faster you go, the harder the interstellar medium holds you back. The ramjet does not accelerate, it brakes, and that, unexpectedly, is useful. Zubrin's magnetic sail came directly out of this failure, because a device that cannot push you forward through the interstellar medium can certainly slow you down, and a starship that has crossed 4 light-years needs nothing more urgently than a brake. There is something instructive in the whole episode. The ramjet was not defeated by engineering difficulty or lack of ambition. It was defeated by an accounting error that took 3 decades to find, in a scheme that had already lodged itself in the public imagination as the way we would go to the stars. Careful arithmetic dismantled it. The same careful arithmetic has been applied to the one fuel that seems to have no flaw at all, the fuel that converts entirely into energy, and it finds a different problem. Not physics. Manufacturing. Every fuel we have ever used converts a fraction of its mass into energy. Burning hydrogen with oxygen converts about 1 part in 10 billion. Fissioning uranium converts about 1 part in 1,000. Fusing hydrogen into helium, the reaction that powers the Sun, converts about 7 parts in 1,000. Matter-meeting antimatter converts all of it. An antiproton is identical to a proton in mass and opposite in charge. Bring them together and both cease to exist, and in their place appear a spray of pions and gamma rays carrying the entire rest energy of both particles, which Einstein's relation gives as mass times the speed of light squared. A single gram of antimatter annihilating with a gram of matter releases roughly the energy of the Hiroshima bomb. Nothing else in physics is remotely this concentrated. For a starship, that means an exhaust velocity approaching the speed of light and a mass ratio that finally becomes reasonable. Serious studies, including work at Pennsylvania State University in the 1990s on antimatter-catalyzed designs, and the Valkyrie concept sketched later by Charles Pellegrino and Jim Powell find that tens of tons of antimatter would send a modest ship to a nearby star at a large fraction of light speed. Some designs need only micrograms, using antiprotons to trigger fission or fusion in ordinary fuel rather than as the primary energy source. We can make antimatter, we do it routinely. At CERN, antiprotons are produced by slamming protons into a metal target, then slowed in a machine called the antiproton decelerator, then combined with anti-electrons to make antihydrogen. In 1995, 9 atoms of antihydrogen were made at CERN and existed for perhaps 40 billionths of a second. In 2010, the Alpha collaboration trapped 38 atoms in a magnetic bottle. In 2011, they held antihydrogen for 1,000 seconds. In recent years, they have measured its spectrum and watched it fall downward under gravity, exactly as matter does. Now, the accounting. The total quantity of antimatter ever produced by all the accelerators on Earth, added together across decades, amounts to a few billionths of a gram. If you annihilated all of it at once, you would boil a cup of tea, roughly. The production process is staggeringly inefficient, wasting something like 1 billion units of energy for every unit stored in the antiprotons, because the collisions that make them scatter everything in all directions and almost none of it can be caught. A NASA estimate once put the cost at around $62.5 trillion per gram, and that figure assumed the machinery would be optimized rather than repurposed from particle physics. To gather 10 tons at current rates would take longer than the universe has existed by a margin of many orders of magnitude. Storage is its own wall. Antimatter cannot touch anything. It must be held as a cold, charged plasma in electromagnetic traps, and the traps must never fail, and the vacuum must be better than the vacuum of space, and the whole apparatus must ride aboard a ship for years. None of this is forbidden. There is no law of nature standing in the way, only a manufacturing problem of a size we have no framework for imagining solving. And that peculiar situation, where the physics permits and the practice refuses, is what pushes the most credible Starship proposals toward a fuel we do not have to make, do not have to carry, and cannot run out of. Light has no mass, and it still pushes. Johannes Kepler noticed in 1619 that comet tails always point away from the sun, whatever direction the comet is travelling, and he guessed that sunlight was blowing them back. He was partly right. James Clerk Maxwell showed in 1873 that electromagnetic waves carry momentum, and in 1900 the Russian physicist Pyotr Lebedev measured the pressure of light in a laboratory on a delicate torsion balance in a vacuum and found it was exactly what Maxwell predicted. The pressure is tiny. Sunlight at Earth's distance pushes on a perfect mirror with about 9 micronewtons per square metre. Spread a sail 1 kilometre on a side, and you get roughly 9 newtons, which is the weight of a bag of sugar in your hand. But it never stops. It costs nothing, and a force that never stops eventually wins against a mass that carries no fuel. Konstantin Tsiolkovsky and his colleague Friedrich Jander wrote about sails in the 1920s. The first one flew in 2010, when the Japanese Space Agency launched Icaros toward Venus, unfurling a square of polyamide film 14 meters on a side and 12 times thinner than a human hair, spun out by weights at its corners. It worked. Instruments confirmed the acceleration, and it steered by changing the reflectivity of patches along its edge. The Planetary Society, a non-profit founded by Carl Sagan, Bruce Murray and Louis Friedman, flew LightSail 2 in 2019, a sail of 32 square meters carried by a spacecraft the size of a loaf of bread. It raised the high point of its orbit by about 2 kilometers, using nothing but sunlight, then slowly spiraled down through the thin upper atmosphere and burned up in 2022. Now push the idea. Sunlight weakens with the square of distance, so a solar sail gets almost all its acceleration in the first months. Close in. A sail launched on a sundiver trajectory, unfurling near the sun where the light is 1,000 times stronger, might leave the solar system at 15 or 20 kilometers per second, better than Voyager and still measured in tens of thousands of years to the nearest star. The fix is obvious and enormous. Do not use the sun. Build your own light. A laser can be aimed. It does not spread and weaken the way sunlight does, not if the beam is large enough and the sail is close enough. Robert Forward, a physicist at Hughes Research Laboratories, who spent his life on exactly this problem, published a design in 1984 for a sail 1,000 kilometers across, pushed by a laser of 65,000 gigawatts focused through a lens built of concentric rings of thin plastic, 1,000 kilometers wide, parked out near Saturn. It carried a crew. It even had a scheme for stopping, splitting the sail into rings so the outer ring could reflect light back onto the inner one and decelerate it. Forward's numbers were honest, and the power requirement was several thousand times the total electrical generation of the human species. He knew that. He was showing that the physics permitted it, and leaving the engineering to a wealthier century. Then, in the 2010s, someone noticed that the equation gets much friendlier if you stop insisting on carrying people, or instruments, or anything heavier than a postage stamp. Shrink the payload far enough, and the laser you need shrinks with it, from thousands of gigawatts down to something a determined civilization could build in a desert. In April of 2016, the physicist Stephen Hawking, the entrepreneur Yuri Milner, and the Facebook founder Mark Zuckerberg announced a $100 million research program called Breakthrough Starshot, chaired by the Harvard astronomer Avi Loeb. Its aim was to establish whether a gram-scale probe could be sent to the Alpha Centauri system at 20% of the speed of light, arriving about 20 years after launch. The spacecraft is called a star chip. It is a wafer, a few centimeters across, weighing about a gram, carrying cameras, a power source, a navigation system, and a laser for talking home, all fabricated as one integrated circuit. Attached to it is a sail a few meters wide, made of some material only a few hundred atoms thick, weighing perhaps another gram. On the ground, a phased array of perhaps 100 million small lasers, spread across a kilometer of high desert, fires together as a single beam of 100 gigawatts. That is roughly the electrical output of 100 large nuclear power stations, delivered for 10 minutes. The sail absorbs almost none of it. Reflection is the entire trick. If the sail absorbed even 1/100%, it would vaporize instantly. During those 10 minutes, the probe accelerates at about 60,000 times Earth's gravity, which is survivable only because there is nothing aboard with organs. It crosses the distance of the moon in a few minutes. When the laser shuts off, it is moving at 60,000 kilometers per second, and it never speeds up or slows down again. 20 years and change later, it crosses the Alpha Centauri system at that same speed. It cannot stop. Its cameras have hours at most to photograph Proxima Centauri b, the planet found in 2016 orbiting the nearest star in the zone where liquid water could exist. Then it sends the images home with a laser the strength of a laboratory pointer, across 4.2 light-years into a receiver back on Earth, and the data arrives 4 years after that. The unsolved problems are catalogued honestly by the project itself. Nobody knows how to make a sail material with the necessary reflectivity, thinness, and heat tolerance. Nobody knows how to keep a sail stable on a beam, since a sail that drifts even slightly off-center will be pushed further off and tumble away. Nobody has built a phased laser array of more than a few kilowatts, let alone 100 gigawatts, and the atmosphere must be corrected for in real time. The cost estimates for the beamer run to $5 or $10 billion, and probably far more, and yet nothing in it violates any law. That is the distinction worth holding. Antimatter fails on manufacturing, the ramjet fails on physics, Starshot fails on engineering, which is the only kind of failure that history has repeatedly overturned. Consider what it would mean if it worked. 20 years of flight, 4 years of light in transit, and a photograph of another world orbiting another sun, taken by an object that weighs less than a paperclip and cost less than a warship. launch 1,000 of them, one a day, and lose most of them, because losing them is the plan. Something will be lost. At 60,000 kilometers per second, interstellar space is not empty enough. The gas between the stars is thin, about 1 atom for every cubic centimetre. Mixed into it, making up roughly 1% of its mass, is dust. These are not the fluffy grey clumps under a bed. Interstellar grains are individual particles, mostly silicates and carbon, formed in the outflows of dying stars and coated with mantles of ice. A typical grain measures about 1/10 of a micrometer across, which is 1,000th the width of a human hair, and there is perhaps one of them in every 100,000 cubic meters of space. You could fly through a cubic kilometer of interstellar space and expect to meet 10,000 of them, which sounds like a great many until you remember how small they are. A Voyager crossing 4 light-years would sweep up a total dust mass of a fraction of a gram, arriving as gentle taps. Speed changes everything, because kinetic energy rises as the square of velocity. At 20% of light speed, that same 1/10 of a micrometer grain arrives carrying about as much energy as a rifle bullet, delivered into a spot smaller than a bacterium. It does not scratch the sail. It punches a clean hole and vaporizes a crater of surrounding material into plasma. A gram-scale star chip, a few centimeters wide, will meet perhaps a handful of grains that size on the crossing, and many millions of smaller ones. The smaller ones erode. Atoms of hydrogen and helium, arriving at 60,000 kilometers per second, strike the leading face like a sandblaster, sputtering material away and heating the surface. Studies by Thiem Huang and Avi Loeb and their colleagues estimated that a graphite surface would lose roughly 0.5 millimeter of thickness on the way, which for a wafer measured in 1/10 of a millimeter is not an inconvenience. It is the end of the mission. The proposed fixes are modest and clever. Fly the chip edge on so the tiny cross-section takes the erosion. Coat the leading edge with beryllium copper, which handles the heat. Accept losses and send a swarm. Daedalus took the opposite approach, carrying 50 tons of beryllium as a shield and firing a cloud of dust ahead of itself to shatter anything larger before contact. None of it makes the problem disappear, because the problem is not a design flaw. It is a statement about the relationship between speed and energy, and it applies to any object moving quickly through any medium. Which brings up an odd asymmetry in this whole story. The interstellar medium is far too thin to slow Voyager 1 down in any meaningful way. Nothing out there will stop it. Over 30,000 years it will lose almost nothing to friction, because there is essentially nothing to rub against. Voyager is safe precisely because it is slow. The dust that ignores it entirely would tear a Starshot probe to pieces. We know these numbers with some confidence now, not from theory but from measurement, because 2 spacecraft are out in that medium taking readings. What they found was not what anyone had drawn on the charts. Voyager 1 carries no working plasma detector, but Voyager 2 does, and when it crossed the heliopause in November of 2018, it began sending back the first direct measurements ever made of the gas between the stars. That gas has a name. The Sun is currently passing through a wisp called the local interstellar cloud, sometimes the local fluff, about 30 light-years across and containing roughly 1/10 of an atom per cubic centimetre, warm by the standards of interstellar space at around 6,700 degrees Celsius. Temperature there means the speed of individual particles, not heat you could feel, because the particles are so scarce that a person floating in it would freeze rather than burn. Voyager 2 measured the cloud's density directly and found it denser than the models had predicted. It measured the temperature of the plasma just outside the heliopause at around 30,000 degrees, several times hotter than expected. And it found something stranger still, a layer just beyond the boundary where the magnetic field piles up and the plasma flows in a direction that no one had drawn on any chart. Both Voyagers found that the magnetic field outside is aligned almost exactly with the field inside, which should not happen if the two are independent. The current best guess is that the fields are connected, draped through one another across the heliopause, and that is not a solved question. It is an open one, being argued over now. The Sun entered the local interstellar cloud somewhere between 40,000 and 150,000 years ago, and it will pass out the other side within the next few tens of thousands of years into a neighbouring wisp called the G Cloud. The clouds are not stationary either. They are moving, driven outward by the expansion of a much larger structure. That structure is the local bubble. It is a cavity in the interstellar medium about 1,000 light-years across, in which the gas is 10 times thinner than the galactic average, and the Sun sits near its centre by coincidence, having wandered in about 5 million years ago. In 2022, a team led by Catherine Zucker at the Centre for Astrophysics traced the young stars and the star-forming clouds on the bubble surface and reconstructed its history. Somewhere around 14 million years ago, a cluster of massive stars in this region began exploding. Perhaps 15 supernovae over millions of years swept the gas outward into a shell, and every nearby region of star formation now sits on that expanding surface. We live inside a cavity blown by dead stars, and the emptiness that makes interstellar travel slightly less hostile is their doing. There is a plain conclusion in these measurements, and it is easy to miss. The boundary of the heliosphere is not a shore beyond which lies open water. It is a place where one thin gas gives way to another thin gas, both of them part of a galaxy, both of them moving, and the Sun is drifting through all of it, carrying its planets and its comets and its 2 working spacecraft. Nothing about that boundary was designed for us to cross, and nothing about the region beyond it is designed for anything alive to survive. Voyager 1 has flown for nearly half a century, and its electronics have suffered almost no damage from radiation because it carries a computer with about 69 kilobytes of memory, built from components with features large enough to see under a decent microscope, hardened deliberately against the radiation belts of Jupiter. A cosmic ray passing through such a chip deposits its charge and moves on. There is nothing to kill. A human body is a different kind of instrument. Outside the Earth's magnetic field, there are 2 hazards. The first is solar particle events, sudden storms of protons flung out by flares, which are survivable behind a few centimeters of shielding and are absent between the stars anyway. The second is galactic cosmic rays, and they are the problem. These are atomic nuclei, everything from single protons up to iron, accelerated by supernova shockwaves to nearly the speed of light. They arrive from every direction at all times. The radiation assessment detector aboard the Curiosity rover measured the dose during its cruise to Mars in 2011 and 2012 inside a spacecraft with normal shielding. It came to about 1.8 millisieverts per day. A person on Earth receives roughly 2.4 millisieverts in a year. Shielding barely helps. When a heavy iron nucleus at relativistic speed strikes an aluminum hull, it shatters, and the fragments are themselves fast, ionizing, and numerous. The shielding produces a shower of secondary particles that can do more biological damage than the original ray. Water and polyethylene are better, because hydrogen breaks the nuclei more cleanly, but to reduce the dose meaningfully you need meters of the stuff wrapped around the crew, which is hundreds of tons, which returns you to Tsiolkovsky's logarithm with a heavier payload. The damage that worries radiobiologists most is not cancer, it is the brain. Experiments at the NASA Space Radiation Laboratory at Brookhaven, exposing rodents to simulated cosmic ray doses, found lasting changes in the structure of neurons, reduced complexity in the branching of dendrites, and measurable deficits in memory and behavior. Work by Charles Lemoli's group at the University of California, Irvine, described persistent inflammation in the brain and impaired learning months after exposure. Now scale it. A journey to Alpha Centauri at 10% of light speed lasts more than 40 years. Nobody has proposed a shield that would keep a crew healthy for that long, and moving quickly makes it worse, because the ship rams into the cosmic rays coming the other way, and their energy in the ship's frame climbs accordingly. Then there is everything else, a closed ecosystem that must not fail for decades with no resupply. Bone loss and muscle wasting and fluid shifts in the head that damage eyesight, all of which show up within months on the space station. A population large enough to avoid inbreeding, which studies suggest means several thousand people, all of them living and dying inside a machine, every part sourced, stocked and repairable without a factory. None of this argues that people can never cross. It argues that the machines are the easy part, and the machines are already almost impossible. There is a final indignity in the arithmetic, and it applies to the machines too. Getting there is not the mission. Telling us about it is the mission, and that turns out to be its own kind of impossible. The transmitter aboard Voyager 1 radiates about 22 watts. That is less than the bulb in a refrigerator. The signal leaves the 3.7 meter dish as a narrow cone, but no beam stays narrow forever. By the time it reaches Earth, having travelled for almost a full day, it is spread across a region far wider than the Earth itself, and the fraction that falls on a receiving antenna is measured in units that have no everyday name. The power arriving at the Deep Space Network's 70-meter dish at Goldstone in California is around a tenth of a billionth of a watt, roughly 100 billion times weaker than the signal a digital watch battery could produce. This is not a metaphor for faintness. It is the actual number, and receiving it requires the antenna to be cooled with liquid helium, so that the thermal noise of the receiver's own electronics does not drown the message. Sometimes several dishes across the globe are combined, their signals added in phase to pull the whisper out. Radio spreads because of diffraction, and the spreading follows the same inverse square law as everything else. Double the distance and the received power drops by a factor of 4. Voyager 1 now returns data at about 160 bits per second, which would take a full day to send a single photograph of the kind your phone takes without thinking. Push this out to interstellar distances. Alpha Centauri is roughly 230 times farther than Voyager 1 is now, which means a signal of the same strength arrives about 50,000 times weaker. A Starshot probe, weighing a gram, cannot carry a 70-meter dish or a nuclear generator. Its plan is to use its own sail, unfurled again as a lens, focusing a small laser back toward the solar system, and to have the receiving array on Earth be the same kilometre-wide installation that launched it. Even then, the data rate is a trickle, and each bit crosses 4 years of empty space before anyone reads it. Consider what this does to the shape of any mission. A crew departing for another star or a probe enters a conversation whose replies take years or decades. A question asked at Alpha Centauri and answered from Earth takes 8.5 years to complete a round trip. There is no assistance, there is no committee. Whatever happens out there is handled by whoever is there, using whatever they brought, and the Voyagers are quietly demonstrating the endgame. Their power falls by about 4 watts a year. By the mid-2030s, at the latest, the last instrument will be switched off, and the last transmission will end. Both spacecraft will continue on their trajectories at the same speed, in the same direction, forever, and there will be no way to know where they are. We will calculate their positions rather than observe them. The gold record on the side will still be there, playable, with instructions etched in symbols, and there will be nobody in a position to check. That is the true cost of distance. Not the fuel and not the years, but the way information thins out until nothing can be sent home at all. Which raises a question that sounds like a joke and is not. If the journey takes 10,000 years, and your descendants build a faster ship in 500, why did you leave? In 2006, an engineer named Andrew Kennedy published a paper in the Journal of the British Interplanetary Society with a title that sounds administrative and an argument that unsettles everything. He called it the weight calculation. The setup is this. Suppose a starship leaves today at the best speed technology allows, aimed at a star 1,000 light-years away, and suppose the voyage will last 50,000 years. Meanwhile, back home, technology continues to improve, as it has for centuries, and the speed of the best available ship grows a few percent a year. Ships launched later travel faster. Some of them will overtake the ship that left first, arrive earlier, and greet its crew as ancient history. Kennedy worked out where the balance falls. If the growth rate of travel speed is high, you should wait. If it is low, you should go. And there is a minimum, a specific moment at which the total time to arrival, counting both the waiting and the travelling, is as small as it will ever be. Leave before it, and you waste your life crawling. Leave after it, and you have wasted the years you spent waiting. He estimated, using historical growth rates in the maximum speed achieved by human vehicles, that the wait for interstellar destinations comes to something on the order of 1,000 years. The argument has a sharp edge in both directions. It says that departing too early is not merely inefficient, it is futile, because the mission will be superseded before it arrives. It also says that waiting is only rational if growth continues, and growth has never been guaranteed. A civilization that always waits for the better ship never builds any ship, and a civilization that stops improving discovers that the calculation has quietly changed while it was being patient. There is an obvious objection, and it is a good one. The growth in vehicle speed since the 1960s has been essentially flat. The fastest spacecraft leaving the Sun today is one launched in 1977. Parker goes faster around the Sun, and nothing goes faster away from it. If the curve has already bent over, then waiting buys nothing, and the weight calculation collapses into a plain instruction. Go now, with what you have. Set that aside and something in the framing still holds. Every proposal in this script, Orion and Daedalus and Starshot, is an answer to the same question, which is not whether we can reach another star, but whether we can reach it before the reaching stops mattering. A probe that arrives after the civilization that built it has ended is a message in a bottle sent by a drowned man. And the destinations themselves are not stationary. Stars move. The one you aim at will not be where you aimed. The trajectory has to account for a target that drifts thousands of kilometers per second sideways across the sky over the centuries of transit. Voyager 1 demonstrates the point without meaning to. It was never aimed at anything. Its path was set by Titan and by Saturn, and where it goes from here is a matter of arithmetic performed after the fact on a machine nobody steered toward a star. Voyager 1 is climbing out of the plane of the planets at about 35 degrees, heading in the general direction of the constellation of Fucus, the Serpent Bearer. Nothing waits for it there. In about 40,000 years it will pass within about 1.6 light-years of a star called Gliese 445, a dim red dwarf currently 17 light-years away in the constellation Camelopardalis. 1.6 light-years is roughly 10,000 times the distance from the Earth to the Sun, far outside anything you could call an encounter. The star will be a bright point. Voyager will not be captured, will not be slowed, and will not be seen. Voyager 2, climbing southward out of the plane, will pass about 1.7 light-years from Ross 248, another red dwarf, in roughly the same 40,000 years. Pioneer 10 is drifting toward Aldebaran in Taurus, and will need something close to 2 million years. Pioneer 11 is aimed generally at Aquila, and takes about 4 million to reach that neighbourhood. New Horizons is headed towards Sagittarius, and will pass near no star at all for a very long time. The most poetic figure in this catalogue is also the most deflating. In about 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in the sky. That is farther than Alpha Centauri is from us right now. Voyager 2's closest approach to the most famous star in the neighbourhood will leave it more distant than a star we can see from a suburban driveway on any winter night. That is the real meaning of the numbers. Interstellar space is not mostly empty. It is entirely empty. A spacecraft crossing the galaxy at random will almost never pass close to anything, because the stars, though numbered in hundreds of billions, occupy a volume so large that the distance between them is millions of times their own diameters. Scale the Sun to a grain of sand and its nearest neighbour is a grain of sand 30 kilometres away. The Voyagers will not be destroyed. There is nothing out there to destroy them. Micrometeoroid impacts will be negligible. Cosmic ray erosion will remove a few atoms over millions of years, and the gold record will remain readable for perhaps 1 billion years, longer than the surface of the Earth will remain habitable. They will orbit the centre of the galaxy, once every 230 million years or so, along with everything else, and they will do this for as long as the galaxy holds together. They are not leaving the galaxy, they are joining the crowd. That is the outcome for objects thrown outward at 17 kilometers per second by an alignment of planets that will not recur in our lifetimes, aimed by accident, carrying pictures of a world that will have changed beyond recognition before the first close pass. Everything humanity has ever launched away from the Sun is destined for a long, quiet circuit of the Milky Way. And there is one detail that ought to be jarring. Objects do this in the other direction too. Things arrive. On the 19th of October 2017, a telescope on Haleakala in Hawaii, part of the Pan-STARRS survey, recorded a faint moving point. Within days, the orbit was clear and it was not an orbit at all. The object was on a hyperbolic path, coming in from above the plane of the solar system at 26 kilometers per second relative to the Sun, whipping around at less than the distance of Mercury and leaving. It had not come from here. They named it Oumuamua, a Hawaiian word suggesting a scout arriving first from far away. It was small, a few hundred meters at most, and it tumbled every 7 or 8 hours in a way that made its brightness vary by a factor of about 10, which implied a shape far more elongated than any asteroid we know. It was reddish. It had no tail, no visible outgassing, and no coma. And it accelerated slightly as it left, in a direction away from the Sun, by an amount too large to explain with sunlight pressure alone, and with no comet dust to show for it. That anomaly is still argued about. The leading explanation involves the sublimation of hydrogen or nitrogen ice that produced no visible dust. Avi Loeb argued publicly that a thin, artificial sheet could not be ruled out. Most astronomers disagree with him, and the object is gone, and nobody will ever check. 2 years later, in August of 2019, an amateur astronomer in Crimea named Gennady Borisov found a second one, and this one was unmistakably a comet, with a tail and a coma and the chemistry of a comet, though unusually rich in carbon monoxide. It came in at 32 kilometers per second and left. 2 visitors in 2 years, found by surveys that were not designed to look for them. That tells you the population is large. Current estimates suggest that at any moment something like 10,000 interstellar objects larger than 100 meters are passing through the region inside Neptune's orbit, and the new Vera C. Rubin Observatory in Chile, which began its survey in 2025, is expected to find many of them. Here is why this belongs in a story about leaving. Every one of those objects was ejected from another star system. Comets in an Oort cloud sit at the very top of a gravity well, moving at a few hundred meters per second, and a passing star or a wandering giant planet needs to nudge them by almost nothing to send them out forever. Our own solar system has probably thrown out more mass in comets than remains in all the planets combined. And rogue planets, whole worlds untethered from any star, drift between the suns in numbers that microlensing surveys suggest may rival the number of stars themselves. Matter leaves star systems constantly, easily, without engines. The universe is porous. The difference is that these objects are not going anywhere in particular, and neither are we. They are simply moving, and given enough time, moving takes you somewhere. Which invites the reverse thought. If we cannot cross the distance to a star, perhaps a star can cross the distance to us. In 2013, the astronomer Ralph Dieter Schultz identified a dim red dwarf about 20 light-years away with a peculiar property. It was barely moving across the sky, which usually means a star is far off, but its light showed it was close. The only way to reconcile the two is if the star is moving almost directly toward us, or almost directly away. It was moving away, fast. Working backward, Eric Mamajek and colleagues found that about 70,000 years ago, this star and its brown dwarf companion had passed through the outer Oort Cloud, coming within about 0.8 light-years of the Sun. That is roughly 50,000 times the Earth's distance from the Sun, inside the region where comets are loosely held. 70,000 years ago, anatomically modern humans were living in Africa and beginning to spread. Somebody, somewhere, may have looked up and seen it, because red dwarfs flare, and during a flare it would have briefly become visible to the naked eye. The star is called Schultz's star. It was the closest known stellar encounter in the Sun's history, and it left almost no trace, disturbing the Oort Cloud so gently that no shower of comets followed. Then look forward. The European Space Agency's Gaia spacecraft, which measured the positions and motions of nearly 2 billion stars, has allowed astronomers to run the neighbourhood forward in time. Corinne Baylor-Jones and others have found the next visitor, a star called Gliese 710, an orange dwarf about 60% the mass of the Sun, currently around 62 light-years away in the constellation Serpens, is falling toward us. In about 1.3 million years it will pass roughly 0.17 light-years from the Sun. That is around 11,000 times the Earth's distance, and it puts the star deep inside the Oort Cloud, closer to the Sun than any known star has ever come. It will be the brightest star in the sky, and it will be moving slowly, and it will stir the comets. Models suggest a modest increase in comet arrivals over the following million years or so, a rise rather than a catastrophe. Sit with what that means. A destination is coming, unbidden, for free, and it will be within reach of a spacecraft of the kind we can already build. Voyager takes 30,000 years to cross the Oort Cloud. Gliese 710 will be inside it. A probe launched to meet it, at Voyager speeds, would need only a fraction of the time we would spend reaching Alpha Centauri. The wait is 1.3 million years. That is the offer. The universe will deliver a star to your doorstep if you can persuade a civilization to remain intact for 200 times the age of agriculture. And in the meantime, the Sun itself is not standing still. The Sun is falling around the centre of the Milky Way at approximately 220 kilometers per second. Compare that to Voyager 1, which is leaving the Sun at 17. The Sun's own motion through the galaxy is more than a dozen times faster than our fastest departure, and every planet, comet and spacecraft is carried along with it. Voyager is not so much escaping as it is slowly drifting to one side of a convoy, moving at extraordinary speed. That speed was hard to measure, because everything nearby moves with us. It was pinned down using radio interferometry, tracking the apparent motion of the compact radio source at the galactic centre, Sagittarius A star, against distant quasars. From here, the Sun takes somewhere between 220 and 250 million years to complete one orbit. That interval is called a galactic year. The Sun has lived about 20 of them. The last time it stood where it stands now, the earliest dinosaurs were appearing. The Sun does not travel a neat circle. It bobs up and down through the galactic disk about every 60 million years, crossing the mid-plane and rising again, and it drifts slowly inward and outward. Its orbit is a rosette, never quite closing. Now think about what escape means in this setting. Suppose a starship somehow left the Sun entirely, with a large surplus of speed, moving at 10% of light speed, 30,000 kilometers per second. That ship has escaped the Sun, and it has not escaped anything else. It is still deep inside the galaxy, still surrounded by hundreds of billions of stars, still bound by a gravitational field that fills 100,000 light-years. The galaxy is the real container. There is a phrase people use that Voyager 1 has left the solar system, and there is a better way to say the same thing. Voyager 1 has stopped being a satellite of the Sun and started being a satellite of the Milky Way. Its orbit around the galactic centre will be almost identical to the Sun's, because it is moving so slowly relative to the Sun that the difference barely matters. Over the next few hundred million years, Voyager and the Sun will circle the galaxy together, separating by only a few light years, occasionally being pulled apart or pushed together by the stars they pass. The gold record will complete laps of the Milky Way alongside the star it was launched from. That is a strange and quiet thing to know. The Great Departure, the machine that left forever, is essentially travelling in company with everything it left behind. It is a passenger on the same enormous carousel. So what would it actually take to step off the carousel? To leave not the Sun but the galaxy itself and cross to another? The number exists, it has been measured, and it is larger than most people expect, and the reason it is larger is that most of the mass doing the holding is mass nobody has ever seen. To escape the Milky Way from where the Sun sits, an object must be moving at somewhere between 550 and 600 kilometers per second relative to the galactic centre. That number comes from measurement. The Rave survey and later the Gaia data have looked for the fastest stars in the solar neighbourhood, and the observed distribution of speeds cuts off sharply because stars moving faster than escape velocity have already left. Reading the position of that cutoff gives the escape speed directly. The best current estimates cluster around 550 kilometers per second. Compare that with the Sun's 220, and with the speed of a hypothetical starship. Escaping the galaxy is not out of reach in the way that antimatter is out of reach. A ship capable of 10% of light speed exceeds galactic escape velocity 100 times over. The obstacle is not speed, it is distance, because the nearest large galaxy, Andromeda, is 2.5 million light-years away, and even at that speed the crossing takes 25 million years. But the escape speed itself contains a revelation. Take the visible matter of the Milky Way, all the stars and gas and dust you can account for by their light, and calculate the escape velocity from the Sun's position. You get a number closer to 200 kilometers per second. The measured value is nearly 3 times higher, which means the galaxy weighs several times more than what shines. This is the same discrepancy Fritz Zwicky found in 1933 when he measured the speeds of galaxies in the Coma cluster and calculated that they were moving too fast for the visible mass to hold them together, and coined a term for the missing material. It is the discrepancy Vera Rubin and Kent Ford established beyond argument in the 1970s by measuring how fast stars orbit in the outer parts of spiral galaxies and finding that the speed does not fall off with distance as it should if the mass ran out where the light does. The Milky Way's visible disk is about 100,000 light-years across and holds perhaps 60 billion solar masses of stars and gas. Around it, extending several 100,000 light-years in every direction, is a halo of something that has mass and does not interact with light, weighing perhaps 1 trillion solar masses. Nobody knows what it is. Decades of underground detectors have not caught a particle of it. So the well we sit at the bottom of is deeper than it appears, and the shape of it was set by matter we cannot see, and this is a pattern that keeps recurring in this story. Voyager escapes the Sun and is held by the galaxy. Escape the galaxy and you are held by the local group, the small collection of galaxies including the Milky Way, Andromeda, the Triangulum galaxy, and dozens of dwarfs bound together by their mutual gravity. Escape the local group and there is nothing holding you at all. And that turns out to be the worst news in this entire script, because the universe beyond the local group is not merely far away, it is leaving. In 1912, at the Lowell Observatory in Flagstaff, Arizona, an astronomer named Vesto Slipher pointed a 24-inch refractor at the Andromeda Nebula and spent hours collecting enough light to spread into a spectrum. The dark lines in that spectrum, the fingerprints of specific elements, sat at shifted positions. Andromeda was rushing toward us at 300 kilometers per second. He kept going. Over the next several years, Slipher measured the spectra of more than 40 spiral nebulae, and almost all of them were shifted the other way. They were receding, and some of them at more than 1,000 kilometers per second, faster than anything then known. Nobody knew what the spirals were. In 1925, Edwin Hubble, using the 100-inch telescope on Mount Wilson, found individual variable stars in Andromeda, whose known brightness revealed their distance and settled it. The spirals are galaxies far outside our own. Then Hubble combined the distances with Slipher's velocities. In 1929, he published the relation that carries his name and which Georges Lemaitre had derived from theory 2 years earlier. The farther away a galaxy is, the faster it recedes, and the relationship is proportional. That is not the signature of an explosion scattering debris. It is the signature of space itself expanding, every distance growing, every galaxy seeing every other galaxy retreat. For most of the 20th century, the assumption was that gravity must be slowing this expansion down, and the only question was whether it would eventually stop and reverse. In 1998, 2 competing teams answered it. One, the High-Z Supernova Search, led by Brian Schmidt and Adam Rees. The other, the Supernova Cosmology Project, led by Saul Perlmutter. Both were measuring the brightness of Type 1 supernovae, which explode with a reliable intrinsic brightness and can therefore be used as distance markers in galaxies billions of light years away. The distant supernovae were fainter than they should have been. Fainter means farther than a decelerating universe would allow. The expansion is not slowing. It has been speeding up for about 5 billion years. The cause was named dark energy, which is a label for an unexplained pressure, a property of empty space that pushes it apart. It amounts to roughly 70% of everything in the universe. The 3 astronomers shared the Nobel Prize in 2011, and the substance they discovered remains entirely unexplained. Within a gravitationally bound system, none of this matters. The local group is held together and will stay together. The Milky Way is not expanding. Your body is not expanding. But every galaxy beyond the local group is receding, and the rate at which each one recedes grows with distance, and dark energy makes that rate accelerate. A galaxy far enough away recedes faster than light, which is permitted, because space is not moving through space. And once a galaxy is receding faster than light can close the gap, a photon leaving it now will never arrive. Not late. Never. Every corner of the sky has a boundary in it, and the boundary has a number. Astronomers call it the cosmic event horizon. It is the distance beyond which anything that happens now will never be seen by us, and it is not the same as the edge of the observable universe. The observable universe is about 46 billion light-years in radius, and it contains everything whose past light has had time to reach us. The event horizon is closer, at around 16 billion light-years, and it marks everything whose future light will ever reach us. Anything outside that radius is not merely far, it is unreachable, permanently, by us, by our signals, and by any ship we could ever build travelling at any speed short of the speed of light, which is to say, at any speed at all. In 2011, the physicists Lawrence Krauss and Robert Scherer, and separately Toby Ord in a paper on the reachable universe, worked through what that means in terms of galaxies. Ord's calculation put it plainly. Of the roughly 2 trillion galaxies in the observable universe, the fraction that a probe leaving Earth today at close to the speed of light could ever reach is around 3%. 97% of the galaxies we can see are already beyond any possible contact. We can see them. Their light left long ago when the gap was smaller, and it is still arriving. But we're watching a departure that has already happened. If a civilization in one of those galaxies transmitted a message this morning, it would travel outward forever without ever crossing the widening space to us. The number is not stable either. It shrinks. Because the expansion accelerates, the horizon draws inward in terms of which galaxies remain reachable, and every year that passes, roughly 100,000 stars pass permanently beyond the boundary of anything we could ever visit. Not because they moved away in any local sense, but because the space between grew. This is what the title of this script actually means, and it is the plainest fact in it. The escape we are discussing is not merely difficult. For most of the universe, it is already over. The deadline passed while trilobites were the most sophisticated things on Earth. Far enough into the future, this reaches its conclusion. In perhaps 100 billion years, everything outside the local group will have receded beyond the horizon. The Milky Way and Andromeda will have merged into a single elliptical galaxy, sometimes called Milkomeda, and the dwarfs will have fallen in with them. An astronomer standing on a planet in that galaxy, with any telescope of any size, will see stars, and beyond the stars, nothing. No other galaxies, no evidence of expansion, no cosmic microwave background stretched to wavelengths too long to detect. They will be able to derive a static, eternal, island universe from perfect observations, and they will be wrong, and they will have no way of knowing it. The evidence for the Big Bang will have left the sky. We are living during the brief window in cosmic history when the truth is still visible, and we're not able to reach any of it. There are closer deadlines than the heat death of the observable sky, and they are the ones with dates. The sun is brightening. As hydrogen fuses to helium in the core grows denser, and to hold itself up it burns hotter. The sun is about 30% more luminous than it was when it formed 4.5 billion years ago, and it gains roughly 1% every 100 million years. That heat drives a chemical cycle in Earth's crust. Warmer rain weathers silicate rock faster, and weathering pulls carbon dioxide out of the atmosphere and locks it into the ocean floor. As the sun brightens, the weathering accelerates, and the carbon dioxide falls. Plants that use the more common photosynthetic pathway begin to starve at around 150 parts per million, and current models by Ken Caldeira and James Casting and others put that point somewhere between 600 million and 900 million years from now. Land plants fail, then the animals that eat them, then the oxygen, which is biological in origin, begins to fall out of the air. Life on Earth has existed for about 3.8 billion years, and it has less than a fifth of that left. The complicated part of it, the part with brains, has considerably less. In about 1 billion years, the oceans begin to evaporate in earnest, and water vapour in the upper atmosphere is broken apart by ultraviolet light, and the hydrogen escapes to space. Earth becomes dry. In perhaps 1.5 billion years, the habitable zone, the band of orbits where liquid water is stable, moves out past Earth and eventually reaches Mars. Around 5 billion years from now, the Sun exhausts its core hydrogen and swells into a red giant, growing to hundreds of times its current size, brightening by a factor of a couple of thousand, swallowing Mercury and Venus certainly, and Earth probably. Then it sheds its outer layers into a glowing shell and leaves behind a white dwarf about the size of the Earth, which cools quietly forever. None of this is a reason to hurry, in the sense of tomorrow. All of it is a reason to be clear about the shape of the situation. Earth is a temporary address, the solar system is a temporary address on a longer lease, and the galaxy is the last address there is, because everything beyond the local group is already receding beyond retrieval. Every star we can ever visit is in this group of galaxies, and every star we can actually plan to visit is in this galaxy, and every star we could reach with anything resembling our present understanding is within a few dozen light years, and the fastest object we have ever launched will not reach any of them. That is the whole account. It is not tragic and it is not hopeful. It is simply the arithmetic of a species that arrived late, in a universe that is coming apart, on a planet with a warming star, with rockets that throw part of themselves backward, wanting very much to be somewhere else. And in the middle of that account, still moving, is a phonograph record. The record is made of copper, plated in gold, and sealed in an aluminum jacket. There are 2 of them, one bolted to each Voyager. Andrewian, Timothy Ferris, Carl Sagan, John Lomberg, Frank Drake, and a small committee assembled the contents in about 6 weeks in 1977, under a deadline that left no time to be careful, which may be why it is so good. On it are 115 images encoded as analog signals, a page of Newton's writing, a woman in a supermarket, a man eating, the chemical structure of DNA. There are greetings in 55 languages, several of them dead. There are sounds of surf, wind, thunder, a chimpanzee, a tractor, a kiss, a mother speaking to her child, and there is 90 minutes of music, chosen with an argument behind every track. The first movement of Bach's Second Brandenburg Concerto, Chuck Berry playing Johnny B. Good, Blind Willie Johnson humming a wordless blues, recorded in 1927 by a man who died of pneumonia after his house burned down and he slept in the ruins, a Navajo night chant, a Peruvian wedding song, a ragga, a men's house song from New Guinea. There is one more track that is not music. Ann Druyan, who was falling in love with Carl Sagan while the record was being made, and who married him 2 years later, went to a laboratory in New York and had her brainwaves, her heartbeat, and the electrical activity of her nervous system recorded for an hour, while she thought about the history of Earth, about what it is to fall in love. That hour is compressed into a minute of sound on the record, and it is out there now, 24 billion kilometers away and moving. Nobody will find it. That is not pessimism. The odds of any object encountering a star system are essentially zero, and there is no reason to expect anyone to be looking, and the record has no beacon, and the aluminum jacket will still be pristine a billion years from now, when the Earth's surface is sterile and the record is somewhere on the far side of the galaxy, having gone around a few times. Sagan understood this. He said the record was really a message to Earth. It was made for us, to be looked at now, as a portrait of a species that took the trouble to describe itself honestly to nobody in particular. The Sun will hold Voyager for another 30,000 years, and then loosely, and then not at all, and the galaxy will hold it for as long as the galaxy exists, and the universe that lies beyond the galaxy has already moved beyond any possibility of reaching. We are held. That was true before anyone wrote an equation about it, and it will be true after the last transmitter falls silent, sometime in the next decade, and Voyager 1 goes on without us, in the dark, at 17 kilometers a second, carrying the sound of a woman's heartbeat, thinking about love in 1977.